Hey chemists, in this crash course we're going to look at acids and bases and just review some of the things you might see on the AP exam. Acidity is measured using what's called pH. That's a measure of concentration. You should know that the pH is the negative logarithm of the H plus concentration that's present in any aqueous mixture that contains an acid or a base. Remember, everything that's aqueous contains both H plus ions and OH minus ions. They're always there as long as water is present. If you have more of the H plus, it's acidic. If you have more of the OH minus, it's basic. And if they're equal to each other, it's neutral. So pH is really just a measure of how concentrated it is. It's a special way of looking at molarity, because all we're doing is taking a molarity and turning it into a different number by taking the negative logarithm. This is different than the pKa, which, even though it is the negative logarithm of the Ka, which goes with an acid, that's a measure of how strong that acid is. So conceptually, those are two very different things. One tells us about the concentration, the molarity of a solution. The other one tells us about the strength. And Ka goes with the chemical compound. It only changes with the temperature, but otherwise it's specific for a chemical compound, an acid. There's also a Kb for bases, but the concept is the same. H plus depends on what that chemical compound is, but also how concentrated it is. What's the molarity? And that can change based on just how much more water you add and what the total volume is. So we'll talk about these as we look at some sample problems. Now there's a specific K value called Kw. This specifically goes for water, and it's equal to the product of the H plus concentration and the OH minus concentration. And at 298 Kelvin, it's always equal to 10 to the negative 14. And we use this a lot to take one concentration and turn it into the other. So you're probably familiar with the fact that each of these is 10 to the negative 7 in pure water at 298 Kelvin, which is how we get a pH equal to 7 in neutral water at 298 Kelvin. But that changes with temperature, and they test us on that a lot, and you'll see that when we look at a sample problem. Okay, I think the best way to review a lot of concepts related to acids and bases is to look at a titration curve, because everything in a titration curve is a review of all the concepts we've learned. So a titration curve is a plot of pH versus the volume of a titrant. So we can plot on the y-axis what happens to the concentration in pH versus, let's say, the volume of base that's been added. And let's look at a generic titration of a weak acid plus a strong base. Let's say I'm titrating the weak acid HF with a strong base hydroxide ion that turns into fluoride plus a water molecule. And that right there is a good segue into reminding us just some things about acid-base reactions. Acids and bases have what are called conjugate pairs. HF and F minus are a conjugate pair because they only differ by an H plus ion. OH minus and H2O are also a conjugate pair because they only differ by an H plus ion. The HF has a Ka value. The conjugate base has a Kb value. In fact, the conjugate pair, Ka of HF times Kb of F minus, is actually equal to Kw. That's true for a conjugate pair, which means if I have the Ka of one species, I can get the Kb of its conjugate just by using Kw. Okay, so what happens when we start with some amount of HF and we slowly add OH minus? Well, the curve in the end will look like this. I'm just going to draw what the overall curve looks like, and we're going to pinpoint what it looks like at the beginning, what it looks like along the way, what it looks like at this point of inflection, and then what it looks like at the end. And we'll see that we come across all different things that we've seen before in acid-base chemistry. Let's zoom in on just what happens at the very beginning. At the very beginning of a titration, the pH only depends on the concentration of the acid itself. We have some molarity of the acid, in this case hydrofluoric acid, and its pH is prior to anything being added. So we're just right here at a zero volume of base. How you get that is you need to know the Ka of HF, and you can set it equal to an expression, x squared, divided by the molarity of that acid. This comes from abbreviating the Rice chart that you would set up with the acid-base equilibrium, and then you solve for x, and x is actually equal to your molarity of H+. I'm not going to go into everything that went into where that came from. You should go back and review how to set up equilibrium and Rice charts, but that's what we can get to. You can go right to that, and that's how you get the H+ concentration and obviously the pH of a weak acid at the beginning. What's going on halfway? Halfway to this equivalence point? Well, after you start and prior to what's called the equivalence point, we're in what's called the buffer region. The buffer region is after you've begun the titration and you've turned some of the weak acid into its conjugate. So you have both HF and F-, and that's what a buffer is. A buffer is a mixture of the conjugate pair. It's always got to have a weak component to it, so this is a perfect example where we have a buffer. And as long as you're in the buffer range, you can use the Henderson-Hasselbalch equation, which is where the pH is equal to the pKa, that's the pKa of the acidic part, in this case the HF, plus the logarithm of the ratio of the concentration of the conjugate base, F-, over the concentration of HF, whatever they are at that point. So you have to do some stoichiometry to figure how much of this has been converted into the fluoride, but luckily it's just 1-to-1. For every equivalent of base that's been added, you've converted the HF into its conjugate base. And as long as we haven't converted all of it, that means you have some amount of HF remaining, and you've generated some amount of F-. And as long as you have an appreciable amount of both, then you are by definition in a buffer, and you get to go right to this equation to figure out the pH. It's based on the Ka of the acid, and then the ratio of the molarities of each part. There's actually another version of this equation that I kind of like a little bit better. It's almost exactly the same, but instead of molarities, it's moles. It's the moles of F- divided by the moles of HF. It's actually the same equation, because if you think about it, you're in a mixture, so the volume is the same. So if you divide by the total volume, you can actually just get rid of those volumes, and you get a different version of this equation. It gets you the same outcome. And that's anywhere after the beginning and prior to the equivalence point. Okay, next up, now we're at what's called the equivalence point. The equivalence point is when you've converted all of the starting acid into its conjugate. So there's no more HF. You're now exclusively at the conjugate base, which really means the pH is based on the pH of the salt. A salt is just a weak acid or a weak base. So if you learned about salts in your class and their acidic and basic properties, that's because salts just behave as weak acids or weak bases. Here we're making F-. There's some counter ion, maybe a sodium ion or a potassium ion that was there from the beginning of the strong base, and now it's paired up with this. But to get the pH of the salt, that means I need the K value that goes with what that ion is. So I would have to use Kb, this time of the conjugate of F-, and I set up the same expression that we did in the beginning. It's x squared divided by whatever the molarity of that conjugate base anion is. Although this time I have to make a note, because it's Kb, the x is my molarity of hydroxide. Kb always shows a way of making hydroxide. Ka is always a way of making H+, and you have to use the right K value depending on what you're in. Are you in an acid or are you in a base? So how do I get the pH from hydroxide concentration? Well, there is such a thing as a pOH, and it's the negative logarithm of the hydroxide concentration. And then pOH plus pH is equal to 14. So all of these are related to each other, but that's what you do when you're at what's called the equivalence point. It's different than the buffer region. The buffer region has an appreciable amount of both, as opposed to the very beginning, which is just the starting acid, and the equivalence point, which is just the conjugate base. Sometimes halfway to the equivalence point, right in the middle of the buffer region, they call it the halfway point. And that just means the amount of HF you started with has been converted to half of the F minus, which actually means this is a 1-to-1 ratio, and the pH is equal to the pKa, specifically at the halfway point. I'm not going to add that to it. It just gets too crowded. But that's a review of weak acid turning into pH, buffers turning into a pH, and even a conjugate base, aka a salt, turning into a pH. What about way at the end of the titration? What do we do up here? Well, now we're excess hydroxide, so the pH depends on excess hydroxide. And that means I have to figure out how much hydroxide is remaining if for whatever reason I over-titrated this and went past the equivalence point all the way into this region of very, very high pH, very, very basic pH. And that's because let's say I had 10 millimoles of HF. If I, for some reason, used 20 of this, you would convert all of the HF and you'd be down to now 10 leftover millimoles of hydroxide. And you could figure out how much hydroxide that is. And we'll see that in a problem later on. So that's a titration of a weak acid. Just for fun, let's turn this around and see what this would look like if we had the titration of a weak base. I'll draw another titration curve and just show what it would look like if we had the pH of a weak base instead of a weak acid. For example, ammonia plus a strong acid to make the conjugate ammonium. This means I'd be adding acid along the way, and everything is analogous to what we just saw, but it's just going to be flipped upside down. So I'll start with a high pH, have an acidic equivalence, and then a very strong acid at the end. And I'll highlight the points at the beginning, somewhere in the buffer range, an equivalence point, and then all the way at the end, and we can make sense of all of these. First of all, what do we do in the very beginning? Well, in the very beginning, our pH is going to be based on just the weak base. Bases have a Kb value, so Kb is equal to x squared over our concentration of the ammonia. This is a Kb value, so that means my x is equal to a hydroxide concentration as opposed to an H+. I just have to keep track of that. I can always use this expression, K equals x squared over the molarity, but I have to pay attention. Is it a Kb, and x is hydroxide, or is it a Ka, in which case x is an H+? Moving down to the buffer range, good news, it's the same exact equation. The buffer equation still works. It's the pKa plus the log of the base ammonia over the acid ammonium. I have to figure out what those values are, and I have to note that the pKa refers to the Ka of ammonium, the acid part, the one with the extra H. Going to the equivalence point, the equivalence point is still based on the conjugate. Remember, equivalence means I've converted all of the starting material into the conjugate. No more ammonia. I'm now all in ammonium. So the ammonium has a Ka value. In other words, it's the salt, and it's equal to x squared over the concentration of ammonium. This is a Ka, So my X is a H plus concentration, and I can turn that into a pH. And then we get to the very end, and it's going to be based on your excess H plus. So this is sort of analogous to everything we saw earlier in the weak acid titration. We're just starting with a weak base, so I just flip everything around, except for the buffer equation. That always works. And I can solve for the pH at any of these points along the way. I'll just wrap up this review before we do some practice problems and mention one thing that they talk about a lot on the AP exam. It's called the percent ionization. The percent ionization conceptually refers to what happens if you have an acid which dissociates into an H plus ion and an A minus ion. That's actually what the K goes with. And Ka is equal to H plus A minus all over HA. That's why we say it's X squared over the concentration of the acid. The ionization is equal to whatever we end up calculating for the H plus value divided by the original molarity and then multiply by 100. That's how you calculate it. But conceptually, they talk about this quite a lot in terms of what happens when we perturb this equilibrium. For example, most often, what happens if we add water? If you add water to this, if you add a lot of water, think about what that does to the equilibrium constant expression. And what that means is I get to write out my Q. Anytime you perturb something a la Le Chatelier's principle, it's always a good idea to think about what happens to the reaction quotient, the Q value for this. Let's say I added water so that every molarity got cut in half. That means the A minus gets cut in half, the HA gets cut in half, can't really write it that way, and the H plus gets cut in half as well. So every molarity decreases. That means that the Q, if I simplify this, which you can, we could get rid of some of these divide by 2's, like those two. That means the Q is all of a sudden smaller than K. So if I go back to the equilibrium, we just deduced that Q is smaller than K, and if I write K first, it reminds me of that trick where the greater than or less than sign becomes an arrow. So if I add water to this, it shifts the equilibrium forward. It dissociates more. Remember, when Q is less than K, that will cause the equilibrium to favor the forward reaction in order to re-equilibrate. So if you get more forward reaction, that means you're getting more H plus and less H minus. So if H plus increases and HA decreases, that means your percent ionization increases overall, and that would be a justification for that as well. Very common thing that shows up on the AP is how is percent ionization affected by adding water, and you can use the Q expression to explain that. All right, that's a very busy crash course review to remind you of lots of things related to acids and bases. Let's look at some practice questions to see if we can make sense of how to use some of these concepts. I spy percent ionization right away. So here's a table with some weak acid with a small Ka value at different molarities. Notice at different molarities, the H plus concentration changes because molarity depends on molarity. But K is a constant. It goes with the acid. Which one is true for a hypothetical 0.125 molar solution? In other words, something that's in between these two molarities. Scanning the choices, they want me to compare how the percent ionization, the H plus concentration, and the resultant pH depend or compare with either the 0.15 or the 0.1 molar. So if I compare a 0.125 with the 0.15 molar solution, the percent ionization is going to be in between. It's going to be probably around 4. So compared to 0.15, it would be larger. That's true. It would be about 4. It would have also, in between these molarities, it would have a lower H plus concentration. That's true. But if the H plus concentration is lower, that actually means pH would be higher, not lower. So A is an incorrect statement. If I look at B, we're also comparing with the 0.15 molar. We've already said the percent ionization would be larger. The H plus concentration would also be smaller. And then that means the pH would be higher, but that would imply that the pH is lower. So this is also an incorrect statement. We have not hit a correct one yet. Now let's compare it with the 0.1 molar solution. Okay, so compared to 0.1 molar, still in between these two values, but comparing with this row, I just have to pay attention. This question is somewhat tricky because I really have to pay attention to what they're asking. Compared to the 0.1 molar solution, the percent ionization would be in between. That would be smaller than 4.2, so that's correct. The H plus concentration should be higher than 4.2, so a larger H plus concentration. If H plus goes up, that means pH goes down. That means pOH goes up. So actually, I think all three of these are correct, and it looks like C is our correct answer. Just for completeness, since this is review time and we can take our time, let's check the fourth choice and make sure it's incorrect. Well, the smaller percent ionization we've already talked about. The larger concentration of H plus we've already talked about. That's also true. And if the H plus is larger, pH would be smaller. That's incorrect. So narrowed it down to C. Looks like C is the correct answer. Let's try another multiple choice. Here is a weak acid titration with a strong base. Which species is present in greatest concentration after 6 milliliters of KOH has been added? So I find 6 milliliters, I go to the graph, and I highlight that point. This is the buffer region. I know that that's where I am. Which species is present most specifically there? Well, look at where the equivalence point is. The equivalence point happens to be at 10 milliliters. That means that the halfway point is at 5 milliliters. So the halfway, which is just half of the volume of equivalence in this case, that's where the concentration of the weak acid, in this case HNO2, is equal to the concentration of its conjugate base. That's what's always true at the halfway point. So the point they're talking about is past the halfway point. Notice it is at a greater pH. It is more acidic than the halfway. Sorry, less acidic. This is less acidic, aka more basic, than halfway. So conceptually, if the halfway point is where they're equal to each other and we are now more basic, that simply means you have more of the basic part of the buffer. In other words, the conjugate base of the starting species. So the correct answer must be the conjugate base, NO2 minus. There's no significant amount of strong species when you're in the buffer region. HNO2 would be the correct answer if they asked us what's true prior to the halfway point. But in this case, the right answer is C. One more multiple choice. The autoionization of water is endothermic. There's the autoionization of water, two water molecules reacting with each other to make an hydroxide ion and a hydronium. And indeed, it is endothermic. That's a good concept just to sort of commit to memory. I'm going to abbreviate the ionization of water as an H plus ion instead of a hydronium. You'll notice they use hydronium quite a bit, but I like to abbreviate it as H plus. It's just an abbreviation of it. You don't actually have H plus ions, but it's an abbreviation of it, and they're fine with you using that. This is an endothermic process. That means heat is a product. As you heat up water, it ionizes more. You get more dissociation of the ions in hot water compared to cold water. If you just picture this, here's a beaker of cold water. Here's a beaker of hot water. The hot water has more ions in it, not a lot, than the cold water. They're both still neutral. That's always true. Because remember, neutrality means the molarity of each one is the same as each other. It doesn't mean that the numerical value is the same, but it means that they have the same amount of each. So water, when it's pure water, is always neutral no matter what temperature we're talking about. It's just more dissociated. That means the concentrations are different individually. So maybe at 298 Kelvin, let's say our cold one is 298 Kelvin, your pH is 7. If you have hot water, let's say we're 398 Kelvin, it's more concentrated in H+. That actually means your pH is going to be less than 7, but that does not mean it's not still neutral. It's still neutral, you just have more ions present than before. They talk about this concept a lot, but it's important to remember that that's true. So the pH, and here we go, the pH at 25 Celsius is 7, but it's much lower at 100 degrees Celsius. Look at that. That's exactly what we were just talking about, which explains this. Well, at higher temperatures, water dissociates less? No, we just talked about how that's not true. At higher temperatures, water dissociates less? No, not true. C, at higher temperatures, water dissociates more. That's a true statement, but then they say H+ is more than OH-? No, not true. They are equal to each other. So water is still neutral. We can look for that right there. Whoops, I accidentally circled C, but C is incorrect. D is correct. Water is still neutral because the concentrations are equal to each other. Okay, lastly, let's look at a free response question. A student titrates hydrochloric acid with sodium hydroxide. This is a strong acid with a strong base. So notice we have a neutral equivalence point right at a pH of 7. No surprise there. Which species is the proton acceptor? The proton acceptor is another word for a base. So the base is the sodium hydroxide. So we could write NaOH, or more appropriately, just the actual thing that's doing it, hydroxide ion. B, the titration is shown below. Actually, it's over here to the right. Place an X at the equivalence point. There it is. It's the point of inflection right at 20 milliliters. Makes sense. 20 milliliters of 0.1 molar HCl will require 20 milliliters of 0.1 molar NaOH, because at the equivalence point, the moles of each reactant is the same. C, the student repeats this, but they start with 20 milliliters of twice the molarity of HCl. On the same graph, draw the expected titration curve. Well, if they double the molarity, you're doubling the moles. So now it's 2 times the moles of H+. That means I'm going to need twice as many moles of the sodium hydroxide. Same molarity, so that means I need twice the volume. So my new titration curve is going to have an equivalence at 40 mils. It's going to require double the volume. My pH should start the same. It should also increase nonlinearly and eventually end pretty much the same when you're in excess base. So I'll trace a rough curve that has a sharp incline at 40 and ends right about there. That's probably what they're looking for. Starts the same point, increases nonlinearly, an equivalence point still pH 7, but new equivalence at 40. That's got to be how they grade that question. Lastly, here is a particle diagram of the 1 molar HCl. What does the 0.2 molar HCl look like? Notice it's totally dissociated. So I see 4 what look like chloride ions as empty circles and 4 H pluses as filled circles. I just need to double all of those. So we're going to draw the original 4 chlorides, and let's just add 4 more, sort of sporadically around. I also had 4 original H pluses, and let's add 4 more. 1, 2, 3, 4, just randomly spaced. They're probably looking for just twice the number in the same volume because it's twice as concentrated. Okay, that was a lengthy refresher on lots of stuff related to acid-base chemistry. Very big topic commonly seen on the AP. Hopefully this was a useful review.